GLONASS, acronym for Globalnaya navigatsionnaya sputnikovaya sistema, or Global Navigation Satellite System, is a space-based satellite navigation system operated by the Russian Aerospace Defence Forces. It provides an alternative to global positioning system and is the only alternative navigational system in operation with global coverage and of comparable precision. Development of GLONASS began in the Soviet Union in 1976. Beginning on October 12, 1982, numerous rocket launches added satellites to the system until the Constellation was completed in 1995. After a decline in capacity during the late 1990s, in 2001, under Vladimir Putin's presidency, the restoration of the system was made a top government priority and funding was substantially increased. GLONASS is the most expensive program of the Russian Federal Space Agency, consuming a third of its budget in 2010. By 2010, GLONASS had achieved 100% coverage of Russia's territory, and in October 2011, the full orbital constellation of 24 satellites was restored, enabling full global coverage. The GLONASS satellites' designs have undergone several upgrades, with the latest version being GLONASS K. History. Inception and design. The first satellite-based radio navigation system developed in the Soviet Union was Tsiklan, which had the purpose of providing ballistic missile submarines a method for accurate positioning. 31 Tsiklan satellites were launched between 1967 and 1978. The main problem with the system was that, although highly accurate for stationary or slow-moving ships, it required several hours of observation by the receiving station to fix a position, making it unusable for many navigation purposes and for the guidance of the new generation of ballistic missiles. In 1968–1969, a new navigation system, which would support not only the Navy, but also the air, land and space forces, was conceived. Formal requirements were completed in 1970. In 1976, the government made a decision to launch development of the Unified Space Navigation System GLONASS. The task of designing GLONASS was given to a group of young specialists at NPOPM in the city of Krasnoyarsk 26. Under the leadership of Vladimir Putin, they developed different proposals, from which the institute's director Grigory Kranilovsky selected the final one. The work was completed in the late 1970s. The system would consist of 24 satellites operating at an altitude of 20,000 km in medium circular orbit. It would be able to promptly fix the receiving station's position based on signals from 4 satellites, and also reveal the object's speed and direction. The satellites would be launched 3 at a time on the heavy-lift Proton rocket. Due to the large number of satellites needed for the program, NPOPM delegated the manufacturing of the satellites to PO Polyot in Omsk, which had better production capabilities. Originally, GLONASS was designed to have an accuracy of 65 m, but in reality it had an accuracy of 20 m in the civilian signal and 10 m in the military signal. The first-generation GLONASS satellites were 7.8 m tall, had a width of 7.2 m, measured across their solar panels, and a mass of 1,260 kg. Achieving full orbital constellation, in the early 1980s, NPOPM received the first prototype satellites from PO Polyot for ground tests. Many of the produced parts were of low quality and NPOPM engineers had to perform substantial redesigning, leading to a delay. On October 12, 1982, 3 satellites, designated Cosmos 1413, Cosmos 1414, and Cosmos 1415 were launched aboard a Proton rocket. As only one GLONASS satellite was ready in time for the launch instead of the expected 3, it was decided to launch it along with 2 mock-ups. The American media reported the event as a launch of 1 satellite and 2 secret objects. For a long time, the Americans could not find out the nature of those objects. The Telegraph Agency of the Soviet Union covered the launch, describing GLONASS as a system created to determine positioning of civil aviation aircraft, Navy transport and fishing boats of the Soviet Union. From 1982 through April 1991, the Soviet Union successfully launched a total of 43 GLONASS-related satellites plus 5 test satellites. When the Soviet Union disintegrated in 1991, 12 functional GLONASS satellites in 2 planes were operational. Enough to allow limited usage of the system, the Russian Federation took over control of the Constellation and continued its development. In 1993, the system, now consisting of 12 satellites, was formally declared operational, and in December 1995, the Constellation was finally brought to its optimal status of 24 operational satellites. This brought the precision of GLONASS on par with the American GPS system, which had achieved full operational capability th-degree year earlier. Economic crisis and fall into disrepair. Since the first-generation satellites operated for 3 years each, to keep the system at full capacity, 2 launches per year would have been necessary to maintain the full network of 24 satellites. However, in the financially difficult period of 1989–1999, the space program's funding was cut by 80% and Russia consequently found itself unable to afford this launch rate. After the full complement was achieved in December 1995, there were no further launches until December 1999. As a result, the Constellation reached its lowest point of just 6 operational satellites in 2001. As a prelude to demilitarization, responsibility of the program was transferred from the Ministry of Defense to Russia's civilian space agency Roscosmos. Renewed efforts in modernization. In the 2000s, under Vladimir Putin's presidency, the Russian economy recovered and state finances improved considerably. Putin himself took special interest in GLONASS, and the system's restoration was made one of the government's top priorities. For this purpose, on August 2001, the federal targeted program Global Navigation System 2002-2011 was launched. The program was given a budget of $420 million and aimed at restoring the full constellation by 2009. On December 10, 2003, the second-generation satellite design, GLONASS-M, was launched for the first time. It had a slightly larger mass than the baseline GLONASS, standing at 1,415 kg, but it had 7 years lifetime, 4 years longer than the lifetime of the original GLONASS satellite, decreasing the required replacement rate. The new satellite also had better accuracy and ability to broadcast 2 extra civilian signals. In 2006, Defense Minister Sergei Ivanov ordered one of the signals to be made available to civilian users. Putin, however, was not satisfied with this, and demanded that the whole system should be made fully available to everyone. Consequently, on May 18, 2007, all restrictions were lifted. The accurate, formerly military-only signal with a precision of 10 m, has since then been freely available to civilian users. During the middle of the first decade of 21st century, the Russian economy boomed, resulting in substantial increases in the country's space budget. In 2007, the financing of the GLONASS program was increased considerably. Its budget was more than doubled. While in 2006 the GLONASS had received $181 million from the federal budget, in 2007 the amount was increased to $380 million. In the end, 140.1 billion rubles was spent on the program 2001–2011, making it Roscosmos' largest project and consuming a third of its 2010 budget of 84.5 billion rubles. For the period of 2012 to 2020, 320 billion rubles were allocated to support the system. Restoring full capacity, in June 2008, the system consisted of 16 satellites, 12 of which were fully operational at the time. At this point, Roscosmos aimed at having a full constellation of 24 satellites in orbit by 2010, 1 year later than previously planned. In September 2008, Prime Minister Vladimir Putin signed a decree allocating additional 67 billion rubles to GLONASS from the federal budget. Promoting commercial use. Although the GLONASS constellation has reached global coverage, its commercialization, especially development of the user segment, has been lacking compared to the American GPS system. For example, the first commercial Russian-made GLONASS navigation device for cars, ɡlոսpace SGK-70, was introduced in 2007, but it was much bigger and costlier than similar GPS receivers. In late 2010, there were only a handful of GLONASS receivers on the market, and few of them were meant for ordinary consumers. To improve the situation, the Russian government has been actively promoting ɡlոտნաss for civilian use. To improve development of the user segment, on August 11, 2010, Sergei Ivanov announced a plan to introduce a 25% import duty on all GPS-capable devices, including mobile phones, unless they are compatible with ɡlոտნass. As well, the government is planning to force all car manufacturers in Russia to make cars with ɡlոտნass starting from 2011. This will affect all car makers, including foreign brands like Ford and Toyota, which have car assembly facilities in Russia. GPS and phone baseband chips from major vendors Qualcomm, Exynos and Broadcom will support ɡlոտnass in combination with GPS. In April 2011, Sweden's SWEPAS, a national network of satellite reference stations which provides data for real-time positioning with meter accuracy, became the first known foreign company to use ɡlոտnass. Smartphones and tablets also saw implementation of ɡlոտnass support in 2011 with devices released that year from Xiaomi Tech Company, Sony Ericsson, Samsung, Asus, Apple and HTC adding support for the system, allowing increased accuracy and lock-on speed in difficult conditions. For a more complete list of smartphones, see List of smartphones using ɡlոտnass navigation. Finishing the Constellation. Russia's aim of finishing the Constellation in 2010 suffered a setback when a December 2010 launch of 3 ɡlոտნass-M satellites failed. The Proton-M rocket itself performed flawlessly, but the upper stage block DAM-3 was loaded with too much fuel due to a sensor failure. As a result, the upper stage and the 3 satellites crashed into the Pacific Ocean. Kommersant estimated that the launch failure cost up to $160 million. Russian President Dmitry Medvedev ordered a full audit of the entire program and an investigation into the failure. Following the mishap, Roscosmos activated 2 reserve satellites and decided to make the first improved ɡlոտnass-K satellite, to be launched in February 2011, part of the operational constellation instead of mainly for testing as was originally planned. This would bring the total number of satellites to 23, obtaining almost complete worldwide coverage. The ɡlոտnass K2 was originally scheduled to be launched by 2013, however by 2012 was not expected to be launched until 2015. In 2010, President Dmitry Medvedev ordered the government to prepare a new federal targeted program for ɡlոտnass, covering the years 2012–2020. The original 2001 program is scheduled to end in 2011. On June 22, 2011, Roscosmos revealed that the agency was looking for a funding of 402 billion rubles for the program. The funds would be spent on maintaining the satellite constellation, on developing and maintaining navigational maps as well as on sponsoring supplemental technologies to make ɡlոտnass more attractive to users. On October 2, 2011, the 24th satellite of the system, a ɡlոտnass-M, was successfully launched from Plesetsk Cosmodrome and is now in service. This made the ɡlոտnass constellation fully restored, for the first time since 1996. On November 5, 2011, the Proton-M booster successfully put 3 ɡlոտnass-M units in final orbit. On Monday 28 November 2011, a Soyuz rocket, launched from the Plesetsk Cosmodrome Space Center, placed a single ɡlոտnass-M satellite into orbit into Plane 3. On April 26, 2013, a single ɡlոտnass-M satellite was delivered to the orbit by Soyuz rocket from Plesetsk Cosmodrome, restoring the constellation to 24 operational satellites, the minimum to provide global coverage. On July 2, 2013, a Proton-M rocket, carrying 3 ɡlոտnass-M satellites, crashed during takeoff from Baikonur Cosmodrome. It veered off the course just after leaving the pad and plunged into the ground nose first. The rocket employed a Decimeter 03 booster, for the first time since the December 2010 launch, when the vehicle had also failed, resulting in a loss of another 3 satellites. However, as of 2014, while the system was completed from technical point of view, the operational side was still not closed by the Ministry of Defense and its formal status was still in development. System description: ɡlոտნass is a global satellite navigation system, providing real-time position and velocity determination for military and civilian users. The satellites are located in middle circular orbit at 19,100 km altitude with a 64.8-degree inclination and a period of 11 hours and 15 minutes. GLONASS orbit makes it especially suited for usage in high latitudes, where getting a GPS signal can be problematic. The constellation operates in 3 orbital planes, with 8 evenly spaced satellites on each. A fully operational constellation with global coverage consists of 24 satellites, while 18 satellites are necessary for covering the territory of Russia. To get a position fix, the receiver must be in the range of at least 4 satellites. Signals. Fdma. GLONASS satellites transmit 2 types of signal, open standard precision signal L1OF L2OF, and obfuscated high precision signal L1SF L2SF. The signals use similar DSSS encoding and binary phase shift keying modulation as in GPS signals. All GLONASS satellites transmit the same code as their standard precision signal. However, each transmits on a different frequency using a 15-channel frequency division multiple access technique spanning either side from 1602.0 MHz, known as the L1 band. The center frequency is 1602 MHz plus NA. 0.5625 MHz, where N is a satellite's frequency channel number. Signals are transmitted in a 38-degree cone, using right-hand circular polarization, at an EIRP between 25 to 27 dBW. Note that the 24-satellite constellation is accommodated with only 15 channels by using identical frequency channels to support antipodal satellite pairs, as these satellites will never be in view of an Earth-based user at the same time. The L2 band signals use the same Fdma as the L1 band signals, but transmit straddling 1246 MHz with the center frequency 1246 MHz plus NA, 0.4375 MHz, where N spans the same range as for L1. In the original GLONASS design, only obfuscated high-precision signal was broadcast in the L2 band, but starting with GLONASS M, an additional civil reference signal L2OF is broadcast with an identical standard precision code to the L1OF signal. The open standard precision signal is generated with modulo 2 addition of 511 kbits pseudo-random ranging code, 50-bit S navigation message, and an auxiliary 100 Hz meander sequence, all generated using a single time frequency oscillator. The pseudo-random code is generated with a 9-stage shift register operating with a period of 1 millisecond. The navigational message is modulated at 50 bits per second. The superframe of the open signal is 7500 bits long and consists of 5 frames of 30 seconds, taking 150 seconds to transmit the continuous message. Each frame is 1500 bits long and consists of 15 strings of 100 bits, with 85 bits for data and checksum bits, and 15 bits for time mark. Strings 1 to 4 provide immediate data for the transmitting satellite, and are repeated every frame. The data include ephemeris, clock and frequency offsets, and satellite status. Strings 5 to 15 provide non-immediate data for each satellite in the constellation, with frames I for each describing 5 satellites, and frame V describing remaining 4 satellites. The ephemerides are updated every 30 minutes using data from the ground control segment. They use Earth-centered Earth-fixed Cartesian coordinates in position and velocity, and include lunisolar acceleration parameters. The almanac uses modified Keplerian parameters and is updated daily. The more accurate high-precision signal is available for authorized users, such as the Russian military, yet unlike the USP-Y code which is modulated by an encrypting W code, the GLONASS restricted use codes are broadcast in the clear using only security through obscurity. The details of the high-precision signal have not been disclosed. The modulation of the data bits on the L2SF code has recently changed from unmodulated to 250-bit S-burst at random intervals. The L1SF code is modulated by the navigation data at 50-bit S without a Manchester meander code. The high-precision signal is broadcast in phase quadrature with the standard precision signal, effectively sharing the same carrier wave, but with a 10 times higher bandwidth than the open signal. The message format of the high-precision signal remains unpublished, although attempts at reverse engineering indicate that the superframe is composed of 72 frames, each containing 5 strings of 100 bits and taking 10 seconds to transmit, with total length of 36,000 bits or 720 seconds for the whole navigational message. The additional data are seemingly allocated to critical lunisolar acceleration parameters and clock correction terms. Accuracy. At peak efficiency, the standard precision signal offers horizontal positioning accuracy within 5 (10 meters, vertical positioning within 15 meters, a velocity vector measuring within 10 centimeter per second, and timing within 200 nanoseconds, all based on measurements from 4 first-generation satellites simultaneously. Newer satellites such as GLONASS improve on this. GLONASS uses a coordinate datum named PZ90, in which the precise location of the North Pole is given as an average of his position from 1900 to 1905. This is in contrast to the GPS's coordinate datum, WGS84, which uses the location of the North Pole in 1984. As of September 17, 2007, the PZ90 datum has been updated to version PZ90.02, which differ from WGS84 by less than 40 cm in any given direction. Since December 31, 2013, version PZ90.11 is being broadcast, which is aligned to the International Terrestrial Reference System at epoch 2011.0 at the centimeter level. Cdma. Since 2008, new Cdma signals are being researched for use with GLONASS. According to preliminary statements from GLONASS developers, there will be 3 open and 2 restricted Cdma signals. The open signal L30C is centered at 1202.25 MHz and uses BPSK, 10, modulation for both data and pilot channels. The ranging code transmits at 10.23 million chips per second, modulated onto the carrier frequency using QPSK within phase data and quadrature pilot. The data is error-coded with 5-bit Barker code in the pilot with 10-bit Newman-Hoffman code. Open L10C and restricted L1SC signals are centered at 1600.995 MHz, and open L20C and restricted L2SC signals are centered at 1248.06 MHz, overlapping with GLONASS Fdma signals. Open signals L10C and L20C use time division multiplexing to transmit pilot and data signals, with BPSK, 1, modulation for data and BOC, 1, modulation for pilot. Wideband restricted signals L1SC and L2SC use BOC modulation for both data and pilot, transmitted in quadrature phase to the open signals. This places peak signal strength away from the center frequency of narrowband open signals. Binary phase shift keying is used by standard GPS and GLONASS signals, however both BPSK and quadrature phase shift keying can be considered as variations of quadrature amplitude modulation, specifically QAM2 and QAM4. Binary offset carrier is the modulation used by Galileo, modernized GPS, and Compass. The navigational message of the L30C signal is transmitted at 100 bit s. The navigational frame is 15 seconds long and includes 5 strings of symbols each taking 3 seconds. A frame contains ephemeridis for the current satellite and part of the almanac for 3 satellites. The superframe consists of 8 navigational frames, so it takes 120 seconds to transmit 12,000 bits of almanac for all current 24 satellites. In the future, the superframe will be expanded to 10 frames or 15,000 bits of data to cover full 30 satellites. The system time marker is transmitted with each string. UTC leap second correction is achieved by shortening or lengthening the final string of the day by 1 second, with shortened strings being discarded by the receiver. The strings have a version tag to facilitate forward compatibility. Future upgrades to the message format will not break older equipment, which will continue to work by ignoring new data, but up-to-date equipment will be able to use additional information provided by newer satellites. GLONASS K1 test satellite launched in 2011 introduced L30C signal. The final GLONASS-M satellites launched in 2014 to 2017 will also include L30C signal. GLONASS K2 satellites, to be launched in 2015, will feature a full suite of modernized Cdma signals in the existing L1 and L2 bands, which includes L1SC, L10C, L2SC, and L20C, as well as the L30C signal. GLONASS K2 should gradually replace existing satellites starting from 2017, when GLONASS-M launches will cease. GLONASS KM satellites will be launched by 2025. Additional open signals are being studied for these satellites, based on the same frequencies and formats as GPS signals L5 and L1C and corresponding Galileo compass signals E1, E5A and E5B. These signals include: the open signal L10CM will use BOC 1 modulation centered at 1575.42 MHz, similar to modernized GPS signal L1C and Galileo compass signal E1. The open signal L50CM will use BPSK 10 modulation centered at 1176.45 MHz, similar to the GPS safety of life and Galileo compass signal E5A. The open signal L30CM will use BPSK 10 modulation centered at 1207.14 MHz, similar to Galileo compass signal E5B. Such an arrangement will allow easier and cheaper implementation of multi-standard GNSS receivers. With the introduction of Cdma signals, the constellation will be expanded to 30 active satellites by 2025. This may require eventual deprecation of Fdma signals. The new satellites will be deployed into 3 additional planes, bringing the total to 6 planes from the current 3, aided by System for Differential Correction and Monitoring, which is a GNSS augmentation system based on a network of ground-based control stations and communication satellites LUCH-5A and LUCH-5B. Additional satellites may use Molniya orbit, tundra orbit, geosynchronous orbit, or inclined orbit to offer increased regional availability, similar to Japanese QZSS system. Satellites. The main contractor of the GLONASS program is joint stock company Reshetnev Information Satellite Systems. The company, located in Zhelezhagorsk, is the designer of all GLONASS satellites, in cooperation with the Institute for Space Device Engineering and the Russian Institute of Radio Navigation and Time. Serial production of the satellites is accomplished by the company PC Polyot in Omsk. Over the 3 decades of development, the satellite designs have gone through numerous improvements, and can be divided into 3 generations: the original GLONASS, GLONASS-M and GLONASS-K. Each GLONASS satellite has a GRAU designation 11F654, and each of them also has the military Cosmos NNN designation. First generation. The true first generation of GLONASS satellites were all 3-axis stabilized vehicles, generally weighing 1,250 kg, and were equipped with a modest propulsion system to permit relocation within the constellation. Over time they were upgraded to Block IA, IB, and IA vehicles, with each block containing evolutionary improvements. 6 Block IA satellites were launched in 1985 and 1986 with improved time and frequency standards over the prototypes, and increased frequency stability. These spacecraft also demonstrated a 16-month average operational lifetime. Block IB spacecraft, with a 2-year design lifetimes, appeared in 1987, of which a total of 12 were launched, but half were lost in launch vehicle accidents. The 6 spacecraft that made it to orbit worked well, operating for an average of nearly 22 months. Block IA was the most prolific of the first generation. Used exclusively from 1988 to 2000, and continued to be included in launches through 2005, a total of 25 satellites were launched. The design life was 3 years, however numerous spacecraft exceeded this, with one late model lasting 68 months. Block II satellites were typically launched 3 at a time from the Baikonur Cosmodrome using Proton K Block DM2 or Proton K BRIS-M boosters. The only exception was when, on 2 launches, an Italian geodetic reflector satellite was substituted for a GLONASS satellite. Second generation, the second generation of satellites, known as GLONASS M, were developed beginning in 1990 and first launched in 2003. These satellites possess a substantially increased lifetime of 7 years and weigh slightly more at 1,480 kg. They are approximately 2.4 am in diameter and 3.7 am high, with a solar array span of 7.2 am for an electrical power generation capability of 1600 watts at launch. The aft payload structure houses 12 primary antennas for L-band transmissions. Laser corner cube reflectors are also carried to aid in precise orbit determination and geodetic research. On-board cesium clocks provide the local clock source. A total of 41 second-generation satellites were launched through the end of 2013. As with the previous generation, the second-generation spacecraft were launched in triplets using Proton K Block DM2 or Proton K Prism boosters. Some were launched alone with Soyuz 2-1B Fregat, third generation. GLONASS K is a substantial improvement of the previous generation. It is the first unpressurized GLONASS satellite with a much reduced mass. It has an operational lifetime of 10 years, compared to the 7-year lifetime of the second-generation GLONASS M. It will transmit more navigation signals to improve the system's accuracy, including new Cdma signals in the L3 and L5 bands which will use modulation similar to modernized GPS, Galileo and Compass. The new satellite's advanced equipment made solely from Russian components will allow the doubling of GLONASS accuracy. As with the previous satellites, these are 3-axis stabilized, nadir pointing with dual solar arrays. The first GLONASS K satellite was successfully launched on February 26, 2011. Due to their weight reduction, GLONASS K spacecraft can be launched in pairs from the Plesetsk Cosmodrome launch site using the substantially lower-cost Soyuz 2.1B boosters or in 6 at once from the Baikonur Cosmodrome using Proton K Prism launch vehicles. Ground control. The ground control segment of GLONASS is almost entirely located within former Soviet Union territory, except for a station in Brasilia, Brazil. The ground control center and time standards is located in Moscow and the telemetry and tracking stations are in St. Petersburg, Ternopil, Inisseysk, and Komsomolsk-na-Amur. Receivers: Septentrio, Topson, CNAV, JAVAD, Magellan Navigation, Noviatl, Leica Geosystems, Hemisphere GPS and Trimble Incorporated produce GNSS receivers making use of GLONASS. NPO Progress describes a receiver called GALS A1, which combines GPS and GLONASS reception. Skywave Mobile Communications manufactures an Inmarsat-based satellite communications terminal that uses both GLONASS and GPS. As of 2011, some of the latest receivers in the Garmin eTrex line also support GLONASS. Garmin also produce a standalone Bluetooth receiver, the GLO, which combines GPS, WAAS and GLONASS. Various smartphones from 2011 onwards have integrated GLONASS capability, including devices from Xiaomi Tech Company, Sony Ericsson, ZTE, Huawei, Samsung, Apple, iPad mini and iPad, HTC, LG, Motorola and Nokia. Status, availability: as of July 13, 2014, the GLONASS Constellation status is, the system requires 18 satellites for continuous navigation services covering the entire territory of the Russian Federation, and 24 satellites to provide services worldwide. The GLONASS system covers 100% of worldwide territory. On April 2, 2014, the system experienced a technical failure that resulted in practical unavailability of the navigation signal for around 12 hours. On April 14 to 15, 2014, 9 GLONASS satellites experienced another technical failure due to software problems. Accuracy: according to Russian System of Differential Correction and Monitoring's data, as of 2010, precisions of GLONASS navigation definitions for latitude and longitude were 4.46 7.38 am with mean number of navigation space vehicles equals 7 8. In comparison, the same time precisions of GPS navigation definitions were 2.00 8.76 am with mean number of NSV equals 6 11. Civilian GLONASS used alone is therefore very slightly less accurate than GPS. On high latitudes, GLONASS accuracy is better than that of GPS due to the orbital position of the satellites. Some modern receivers are able to use both GLONASS and GPS satellites together, providing greatly improved coverage in urban canyons and giving a very fast time to fix due to over 50 satellites being available. In indoor, urban canyon or mountainous areas, accuracy can be greatly improved over using GPS alone. For using both navigation systems simultaneously, precisions of GLONASS GPS navigation definitions were 2.37 euro 4.65 am with mean number of NSV equals 14 euro 19. In May 2009, Anatoly Permenov, the then director of the Russian Federal Space Agency, stated that actions were undertaken to expand GLONASS's constellation and to improve the ground segment in order to increase the navigation definition of GLONASS to an accuracy of 2.8 am by 2011. In particular, the latest satellite design, GLONASS-K, has the ability to double the system's accuracy once introduced. The system's ground segment is also to undergo improvements. As of early 2012, 16 positioning ground stations are under construction in Russia and in the Antarctic at the Bellingshausen and Novolazarevskaya bases. New stations will be built around the southern hemisphere from Brazil to Indonesia. Together, these improvements are expected to bring GLONASS accuracy to 0.6 am or better by 2020. See also: List of GLONASS satellites, List of smartphones using GLONASS navigation, Global Navigation Satellite System Euro the generic phrase for a global satellite positioning system, multilateration Euro the mathematical technique used for positioning, Cicada Euro a Russian satellite navigation system, Aviakonversai Euro a Russian satellite navigation firm. Notes. References. Bibliography, GLONASS Interface Control Document Edition 5.1, 2008, GLONASS Interface Control Document version 4.0, 1998, English, Federal Special Purpose Program Global Navigation System. Russian Federal Government August 20, 2001. Retrieved April 10, 2007. GLONASS Constellation Status for 18.01.08 under the analysis of the Almanac and accepted in IANC. Russian Space Agency. Retrieved January 18, 2008. GLONASS Summary. Space and Tech. Retrieved April 12, 2007. GLONASS Transmitter Specifications. Archived from the original on June 13, 2007. Retrieved April 13, 2007. Gerbel, Greg. Navigation Satellites and GPS PPS Section 2.2. Retrieved April 10, 2007. TH 1/2 n TH micron TH cubed n euro TH degree TH noeth 1/2 TH degree n TH 3/4 n n unflorin TH 1/2 TH 3/4 n n no TH 1/2 TH degree TH squared TH cubed TH degree n TH 1/2 TH degree TH micron TH 1/4 TH 1/2 TH 3/4 TH cubed TH 3/4 TH 3/4 n on euro TH micron TH plus or minus TH n TH micron TH n TH 3/4 NTH n NTH micron TH 1/4 TH micron TH English, integral accessibility of the navigation of ground-based user along the system GLONASS. Russian Space Agency. Retrieved January 18, 2008. India joins Russian GPS system. The Times of India. January 29, 2007. Retrieved April 12, 2007. India to launch 2 Russian GLONASS satellites. MOS News June 27, 2005. Retrieved April 12, 2007. Joint announcement. GPS GLONASS Interoperability and Compatibility Working Group. December 14, 2006. Archived from the original on September 19, 2007. Retrieved April 13, 2007. Kramer, Andrew E. Russia challenges the U.S. monopoly on satellite navigation. New York Times. Retrieved April 12, 2007. Miller, Keith M. A review of GLONASS Hydrographic Society Journal. Archived from the original on October 12, 2007. Retrieved April 13, 2007. Radical change in the air for GLONASS. GPS World. January 22, 2007. Archived from the original on February 10, 2007. Retrieved April 10, 2007. Russia allocates $380 million for Global Navigation System in 2007. MOS News March 26, 2007. Retrieved April 12, 2007. Russia holds first place in spacecraft launches. MOS News March 26, 2007. Retrieved April 12, 2007. Russia launches new navigation satellites into orbit. Space.com/Associated Press. December 25, 2007. Retrieved December 28, 2007. Russian Space Agency plans cooperation with India. MOS News January 12, 2004. Retrieved April 12, 2007. Space Policy Projects World Space Guide, GLONASS. Federation of American Scientists. Retrieved April 10, 2007. THQ THN Florin TH cube THN THNN TH micron TH 1/4 N TH 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 plus or minus N Florin THN Florin N THN Euro TH micron TH TH 3/4 N N TH degree TH square THN and ON N TH TH 3/4 N on Euro TH micron TH plus or minus THN TH micron THN TH 1/4 TH plus or minus TH micron N TH 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 degree N TH 1/2 TH 3/4 English. The services of system GLONASS will be given to users free of charge. RIA Novosti May 18, 2007. Retrieved May 18, 2007. TH Euro TH TH SH TH 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 3/4 TH 1/2 TH degree N N Fo TH square TH N N on TH 1/2 TH degree N Florin TH N Euro TH degree TH square TH TH micron TH 1/2 TH TH micron English, 3Ka GLONASS M have taken off. Russian Space Agency. December 26, 2006. Archived from the original on September 27, 2007. Retrieved December 29, 2006. Uragan. Gunter's Space Page January 16, 2007. Retrieved April 10, 2007. Uragan Navsat. Russian Space Web. Retrieved April 12, 2007. GLONASS News. Retrieved July 31, 2007. External links. Official GLONASS webpage, GNSS webpage including GLONASS, description of GLONASS on the webpage of the International Laser Ranging Service, GLONASS, present, future and past presented on the ILRS Technical Workshop, September 14 Euro 19, 2009, Metsovo, Greece, a homemade receiver for GPS and GLONASS satellites, Navipedia information on GLONASS.